Hey guys, I'm going to be making a video on options with Interactive Brokers with the IB-Insync API. I just want to ask a favor because I'm new to making videos and I'm not sure if these videos are a waste of people's time, if there's any point of me making new videos, that sort of thing. So if you enjoy the video, can you please give me a comment, like, subscribe, whatever. So I just get a feedback if this is actually helpful and if you want me to make new videos, that sort of thing. I would really appreciate it. Thanks. So options. Once you go options, you never go stocks again. I think that's the moral of the story. Options are way, way, way more fun than stocks. But anyways, the moral of the story of what I'm going to teach you is some basic things with options with IB-Insync. First, I'm going to show you guys how to define an option contract, get historical data for that option contract, get the option chains, get market data for the option contract for the options, get the Greeks, implied volatility, and then I want to do a cool exercise where we always hear about like implied volatility and Greeks and that sort of thing. We don't hear that much about like the risk-free rate. So the famous Black-Scholes model has this whole risk-free rate thing. So usually you're taught in the textbooks of like John Hall that the risk-free rate should be like treasury yields, or like let's say it's a short-term option contract like expiring in a month, you should use like 1 month treasury bill. So I'm going to just show you guys how you could maybe reverse engineer the risk-free rate from real data with Black-Scholes formula and also put call parity. So if you guys are not aware of these things, Black-Scholes-Merton formula is the most famous formula in mathematical finance. It's basically the formula for pricing European call and put options. And the put call parity is a famous relationship between European call and put options. So European call and put options, the expiry, of course, there's no early exercise. In real life, we have American call and put options where there is early exercise. And so these formulas are not exact for that. Also, of course, things like volatility is not constant and that sort of thing. But it is a good approximation. And also, American call options are never optimal to exercise early in most circumstances. Of course, there's corner cases. I faced one with like a stock I sold calls on and was early exercised on me way before the expiry, but because there's like a 900% borrow fee, I guess it was optimal to exercise. But textbooks will tell you it's not optimal to exercise non-dividend paying call options, American call options early. So basically those are famous formulas. You can review them if you want. So let's get to the basics. Okay, so first let's connect to IB. You can do IB equals IB. Before that, let's import IB-Insync from IB-Insync. Import star. And I'm very sleep deprived, so I probably shouldn't have been making this video now, but util that start loop is needed for util that start loop is needed for using notebooks. You do IB equals IB, IB.connect. Of course, in your IB gateway, you're going to have a client ID, and in configuration settings, you're going to have the port. So IB.connect, port equals 4001, client ID, let's just use one. I don't have, I'll use 5. Okay, so I'm connected. So how do you define a contract? So first, for a contract, you need obviously a strike, and let's use 200. You need a symbol. Symbol, let's use, equals Tesla. Expiry, let's use next week's call. So we'll do 2023, 12, 15. Okay, So the easiest way to define a contract is to use the options class. So you do call contract equals option, symbol equals symbol, strike equals strike, you have to write the arguments in order if you use this, equals expiry, last date, trade date or contract length equals expiry, strike equals strike. What's more important is write. For call you do C, for put you do P, exchange equals smart, currency equals USD. So that's how you do an option for call. For put, it's the exact same thing, but for write, you have P. Okay. Now let's do the underlying contract. So underlying contract equals stock, symbol equals symbol, exchange equals smart, currency equals USD. Okay. Again, we should qualify the contracts. So what you do at first is you define like enough parameters to kind of uniquely define the contract so it's not ambiguous. And then you do the IB.qualify contract, so it adds things like the unique identifier for the contract ID, local exchange, primary exchange, things like that. So let me show you guys. So I do call contract, put contract, underlying contract, and it gives me, see, I added contract ID and as we said, primary exchange here, multiplier, things like that. Let's also show you that like it attaches to the object. You don't have to like set it equals to something because it attached. See, it added everything. So now let me show you guys how to get historical data. So this is kind of like, one quick thing before is you can define the option contract a little bit differently. If you look at the source code, oops. Let me pull up the source code for a second. So the option contract is actually like a subclass of the main contract class, and you see there's many different types of securities, sec type, stock, option, future, index, all these things. But for the most common ones like stocks and options, you have like subclasses. So like this option class subclasses it, and as you see, like it has like the symbol, a last trade date or contract month, that's the expiry, the write, call or put, currency, strike, whatever. So it's just basically a contract. But the key thing is here it's sec type equals option for the option contract. And as you see, it's here. Sorry. Sec type equals. This is stock. For stock, it's sec type equals stock. And for option, it's sec type equals option. So, and the rest of the things, these are the important things for the contract object. So if you had like something where you like saying like, okay, it could be a stock or an option or whatever, and you wanted to use this construction with the contract class itself, you can do sec type equals opt. Okay, but you shouldn't do that. You should just use the option class. But anyways, I thought it was good to show you guys. So show you guys how to get historical data. So similar to some of my other videos, you can do it for options. But the key thing is like unlike futures, you can only get it for non-expiring contracts. But I'll show you how to get it for contracts that haven't expired. So let's say like last week, the December 1st call, we can't get it because it's expired. So you do like call contract, you do, let me just write everything down, contract equals call contract. And date time, if you do this, it's still like current time. Let's do duration string. Let's do 1 day. Let's do bar size setting. I love 5-second bars, 5 secs. The rest of the things are what to show. Let's do midpoint. You can do trades, bid, ask. You can you can do a trade bid ask. Use regular trading hours equals true. Let's do keep up to date is false. Let me just show you guys how this looks. Bars. You get these bars. Of course, the list of bars. You can view it as a data frame by doing util.df bars. Okay. So like that's how you get it. And because it's the midpoint, you have like the open, high, low, close, but you don't have volume because it's the midpoint of the bid and ask. So let me show you now how to get options chains. I'm not going to go into too much details. I'll make another video, like some sort of video, like on like visualizing options chains or something like that. And I'll go into more detail. But there's this thing called ib.rec. I think it's rec sec def opt params. Okay, and then you can do under what is required. It's required underlying symbol underlying symbol equals underlying contract that symbol. What else do you need? You need foot fop, whatever this thing is called. You leave it blank. Underlying security type equals let's underline security type. Let's make it let's use the underlying contract.sec type. Okay. Oh, sorry, it's already 2 lines. What else do we need? We need underlying con ID equals underlying contract dot con ID. Sorry. Does this work? Yes, you get the option chains. So let's call it chains, and let's make it simple. We'll only look at smart. That should be good for most people's practical purposes. Unless you really need the exchange, you can do like C for C in chains. If C dot exchange, C for C in change. If C dot sorry, I never ran it. That's why I don't have the autocomplete. Change equals smart. I'm very sleep deprived. Sorry. So this will be chain. Chain. Okay. So chain looks like this, and you have the option chain. You have like the underlying contract. You have the expirations. You have like chain dot expirations, and you also have chain dot strikes. And not all these are valid. So I'll show you another video where like I kind of will show you how to get only the valid ones. But this is kind of like how you get like the maximum like cross product of strikes and expirations. That's a way to think about it. But some of these like certain expirations do not have certain strikes, and you can use the ib.qualify contracts with like a list of the cross product of these things to get what is valid and what's not. But I don't want to waste like the flow of this video to talk about that. So I'll show you later how to do that. Now let me show you how to get market data for options. So like this is like tickers. So you do like call ticker equals ib.rec market data, and I do call contract. This is generic tick list. We'll do another video on that, but like for now, let me just show you like default ticker. We'll do ib.request market data. Put contract false, and now you can get like the current market price and stuff like that. You can do like call ticker dot market price. Put ticker dot market price, and let's do the underlying too, even though we don't really need it. Yeah, forget it. Let's just do the calls. So as you see, because Tesla's at way over our strike. What was the strike we used? We said 200. Tesla's way over 200, and the expiry is like a week. So that's why like the price is so cheap for the put compared to the call. Okay, so you can get Greeks by doing this thing. You can do call ticker dot model Greeks, and then look, you get the Greeks. You get like implied, you get delta, option price, gamma, vega, theta, underlying price. So that's how you get the Greeks. And of course, like you also have the implied volatility here. You have like implied vol. So to get implied volatility, you can do like model Greeks dot implied vol. There's also a method called IB dot calculate implied volatility, where you can give it a contract called contract option price and a underlying price, and you can get implied volatility. Do you guys want to check if this matches? So I'll do call contract. I'll do it's stupid because it already has it above, but I'll do call ticker dot model Greeks dot opt price. What do I need? I need option price, and then I need the underlying price. So I do call ticker dot opt Greeks dot model Greeks dot under price. Let's see if this gives us the same answer. It gave us a little bit different of an answer. I don't know why it gave us a different answer, but it gave us a slightly different answer, but very close. 4643269. Yeah, gave us. It's worth figuring out why it's a little bit different, I guess, potentially. Anyways, I thought it would be fun to do an exercise of like reverse engineering the risk-free rate, because lots of times, like I'm in a situation where like I'm trading options, right? And for stocks, it's very easy for me. It's like, okay, if the stock price goes up $1, I make $100, or stuff like that. But for options, it's not necessarily that easy. Like you want to know if the stock goes up $1, how much will the option go up? Or if, let's say I want to sell the option at a certain price, what stock price change do I need? So it's really important to get the risk-free rate. And I want to show you guys two ways to back that out. So first of all, like in all the finance textbooks, you learn you could use like treasury bond rates. So like in practice, I guess like if it's like 1 month to expiry, you would use like the 1 month T-bill. 3 month expiry, you might use a 3 month T-bill. Whatever like fits the expiry time frame, the time to expiry. So let me show you guys how to do it in two different ways. The first way I'm going to show you guys with the Black-Scholes formula, where like we're going to just back out the R, the risk-free rate, and I'm going to use calls for this example, because puts, anyways, for American puts, it could be optimal to exercise early. And then the put call parity, you have this famous formula where it's call price minus put price equals stock price minus strike price discounted. So basically the forward price. Of course, for American options, it's not exact. I want to be crystal clear. But anyways, you can back the R out by solving for it. So this is the cleanest approach, I think. But they give slightly different answers, so let's try both. Okay, so first thing we need something to calculate the Black-Scholes formula, and I already wrote it somewhere, I think. So I'll call it sorry, I have a you guys have all my secret code. If you want to make big money, you look at this code. Okay, I have okay, let's do calls. So let's say I have a Black-Scholes call formula. I have a Black-Scholes call, and we're going to use the Skippy optimization library to find the solve for R, basically. So first thing we need to do is we need to define a function. So this thing will give us the Black-Scholes call formula. You have the stock price, the strike, time to expiry, risk-free rate, and volatility. So in practice, what we need is we need the model price from Black-Scholes, and we need the market price, and we need to solve for R. That's what we really need. So I have a formula for the Black-Scholes call, and then an implied risk-free rate difference. I'm going to also need a function to get time to maturity. So let's have that. I have it handy near me. So what I'm going to do is I'm going to say like, okay, at expiry, 16 is when market closes. I'm going to subtract that from the current time, convert it to number of years because the formula uses years, and that's going to give me the time to maturity. Okay, so let's. So now I have a thing for get the Black-Scholes price, implied risk-free rate difference, time to maturity. So now let's put it all together. To get the implied risk-free rate, this is the difference. I'll call it risk. I'll call it like model to BS difference. Okay. Sorry. I'll call it model to market diff. This is the difference between the model price and the market price with R as the free parameter. We'll have R as a free parameter. So we'll call it model to market diff. Okay. And we have to get time to maturity. So to get the implied risk-free rate, we're going to solve for R, and we're going to have some initial guess. We'll put the initial guess at 5% because that's like the short treasuries these days. So we call this op.Newton means we do Newton optimization to solve. We're going to solve for R. What we need is we're going to need the model to market diff. We're going to need this function. The only thing that's the first thing is the only thing that we didn't specify is R. So as you see, like args, we have everything but R, right? Okay, so let's show you guys how that's done. This is getting a little sloppy. I'm sorry about that, but I can go more in depth, and maybe I'll redo this video, but I'll post it for now. So to get the implied risk-free rate, let's try to see if this works. So let's apply it. Implied risk-free rate. What's the market price? It's ticker call ticker dot model Greeks dot opt price, and then we'll do call ticker dot model Greeks dot unprice, and then the strike we'll do call contract dot strike. Oh, sorry. Call contract dot strike, and then what else do we need? We need the time to maturity. We'll do it's a little ugly, but get time to maturity. What do I need? I need expiry. Our expiry was 2023, 12/15, and I need the current time. So actually, the call ticker has this current time thing, has a current time, and the current time is going to be something called dot time, I think. Dot time, yay, dot time. And that's going to be our time to expiry. And what else do we need? We need the implied volatility. So we're going to use call ticker dot model Greeks dot implied vol. And this gives us the implied risk-free rate, which is 0.42 when this. And if we do like 1 month T-bill, it's 5. No, sorry. Let's use the real data. So what's the 1 month T-bill rate? It's about 5.382%, and this is a little bit higher, I guess, 5.4%. So this thing is a little bit higher, But you know what? It's not that bad. I think like 5.43. This is with Black-Scholes. To do it with the put call parity, we would solve for R in this formula. And so let's show you maybe how to do that. Let's calculate a what should we calculate? So we need to solve for R. So how are we going to solve for R? We need to do basically we need this formula. This is ugly LaTeX, but so we're going to do def get implied risk-free rate put call parity. And what do we need? We need to we need to compute this thing. R equals let's just translate this to actual code. So we need this formula basically. We need negative log stock price minus call minus put price divided by strike over time to maturity. I'll just call it T, something like this. This is what we need. Log of this, and then time to maturity here. That should give us the right formula. So I'll have like S C of C P S K T. And what's nice about this is you don't have the implied volatility in your equation, but we'll return R. And let's see if this actually works. So let's do get implied risk-free rate put call parity. So let's see if this works. We would do we could do like ticker call ticker dot model Greeks dot opt price, and then we could do call ticker. Oh, sorry. I had a real trade in real life working. That opt price, that's the put price, and then we have the underlying price. We can do call ticker dot model Greeks dot und price, and then we can do call contract dot strike, and then we'll do the same time to maturity thing we had here. We had this thing. Log. Oh, there's no log. np.log. Okay. Ooh, something is really wrong. What if we solve? We get. Wait, what was the formula we need to solve for? S minus this thing over K over time to maturity. S. S minus this thing. Oh, I'm off by parentheses. There we go. Should this work? Yay! 546. So it's very similar to this one, maybe a little bit different. Not exactly this thing. Not exactly the 1 month, but like that's a way to maybe back it out if you want to use this and not guess. Anyways, I'll probably remake this video, but if it was helpful, at least leave me a comment or subscribe. Tell me, motivate me to make new videos and to redo this video. Thank you.